personally don't like how they changed the button.
Which
From because now it's like a combo button. Just
how to activate it?
Yeah.
What do you activate?
Before you used to like the smash or
Yeah, that's exactly how they never changed
from the older version of Smash.
No, I've played since Brawl.
Do you have the Switch too?
No.
I don't know what game.
You smack the smash ball, and then when you have your final smash, you tap B.
Yes.
That's it. There's no combo. The combo is tapping one button.
Yeah, I don't know.
And like it depends on the character.
Unless you're
If you're playing Grid Engine, you'd be right next to him. If you're playing Mario or Sim, it's
So
on
how do you
the
activate your smash?
Well, no. It is the button, but like when I played Smash last time, you get that final smash like as it charged up.
Oh, you can turn that on or it's final smash.
Oh.
We'll have to pause it at 5:30. We'll run smash.
Oh, we don't have a
Yeah,
screen.
the wall is
That would help.
There's a way other than the smash.
Loading. All right. If we have a pendulum and we want to make a prediction for like measure it, like we know our, at least we created a couple of different like models for it, right? Equations of motion. So if we have these two like differential equation to describe our equation of motion, what can we measure we can make a prediction and then we can measure it and then have a comparison between the two, because then we just subtract one from the other and we say our model is within so much percent, right? Or so many somethings. What are we going to measure? What can we measure that we can also predict is the question.
Oh, could we like predict that period of the pendulum?
Predict the period, okay, yeah. We can predict a period. How do we measure the period of the pendulum? Stopwatch? And what? Just, what are we timing?
When it makes a full swing back.
Yeah, so start to finish, because it should start here, go to there, and then come back. Something like that. Okay. How many times do you want to measure it? What's going to make it, what would make it accurate? More measurements? How many?
Like 5 times.
5?
Not so many that your resistance becomes a problem.
Oh, okay. Yeah. We'll do like 1 Professor Cooper height pendulum, like 5'9" pendulum. Like that. There we go. And I was trying to figure out where to go for this. I feel like over there is better.
Over the edge.
Yeah, yeah. All right, so we'll make yeah, 5'9", right there. What's the time period for L equals 5'9"? What are we supposed to get? What are we supposed to measure? If our equation of motion is actually representing the physical real world. How do we figure it out?
Circumference
Circumference of circle?
Like that's how much like
they would be traveling.
Yeah.
Like, period.
Yeah.
I don't know. And then like, I don't know.
Yeah, okay. Yeah, we know like generally distance, at least if we know where it starts and where it ends. Is the time period dependent on how far it travels?
I don't think so, because the further up you bring it, the faster it goes.
The faster it's going to come back.
Omega, you're talking about omega root G over L.
Yeah, I think that could be.
That one? Yeah, root G over L. What is that one? What is that? So I said 5.9 over 12, 5.75. What are we calculating? Root G over L. What is that thing?
Maybe with frequency, like how frequent the rotation is.
It is, so it's a unitless frequency for like how many radians. And it's confusing because we're measuring radians for motion, but radians are also describing like how far along we are. So it's not necessarily that that's how many radians per second it's always going to move. It's saying that it will complete one full cycle in 6.28 radians. Kind of weird. At least if so that's like our natural frequency. Natural frequency. Then what the heck's the time period? Or what? Yeah.
Isn't our period, like our period is equal to 1 over frequency. Frequency is the 1 over 2 pi omega. So when was the last time that we solved that period?
1 over 2 pi times omega. Like that? Seems right, right? How did all the, like, unit-wise, what's happening here? Why are there two different frequencies?
Frequencies and hertz.
Yeah, so F is like hertz, the cycles per second. How many like cycles per second we have?
And the time period is how many seconds it takes for it.
Yeah, so then 1 over that frequency is going to give us like time period, the number of seconds per cycle. So now we're getting closer. How do these units all work out? We have like radians, seconds, and then radians per second. Do you know where all this is coming from? Yeah? Where does it, how do they all like, where do I put radian seconds and radian per second?
Radians per second is omega. So when we try
Yep.
to get in terms of frequency, our 2 pi is also in terms of radians. So the radians cancel out. We have 1 over second for our frequency, which is hertz.
Okay.
But when we're doing the period versus seconds.
Yeah. So up here we would have that radian per second. Down here we're saying 2 pi radian per cycle. So every cycle is 2 pi radians. So then overall we end up with F equals some omega over 2 pi cycles per second. So then T is 2 pi over omega seconds per cycle. Kind of formally going through, like, how do you get from one to the other? Why are they not the same? They're close, but just slightly different, just off by 6. Okay, so then what's the natural frequency? What's 32 over 5.75? 2.37. All right, so then do we want to go straight into time period or get cycles per second first? Whatever you want to do. So which one do we need first? F or T? We can go straight to T, it doesn't matter. At least to me it doesn't matter, but. Okay, what's capital T, our time period? 2.65 seconds?
Yes.
All right. Cool. Now we'll do, let's see, get this one. Keep going over here. See if that works. I think that'll work. Good. All right, so I'll get it swinging, and then we gotta measure, then we gotta count out the number of cycles. How many cycles do we wanna add up before we divide by time? Can you see it? No. This way. What do we think? 100? 5 or 10? 10's good, because then we just, if we end up getting like 26 seconds, then we just move it over, right? Okay. How many timers do we have? 1, 2, 3. All right, so what I'll do, we'll get it start swinging, and then we'll start counting once it like gets up to the top somewhere. Okay, ready? 1, 2, oh, no? I got it. 3, 4, 5, 6, 7, 8, 9, 10. How's that? 24. 26.8. Alright, so now we have multiple times, right? Alright, so let's write down what time you have so far.
6-1. I was like counting down to almost start the timer. Explain what this was.
Alright, what measurements do we have? 27 what? 26.83, 26.99, 24.35, what else? 26.7, 23.9, oh man.
You guys just,
Yeah. 26 point what?
It's okay.
26.11.
You saw it coming up and you were like, that's the top.
Good?
Yeah, 27.14.
Oh, 27.14. All right, so our
Ruining the data. Look at that 26.9.
You're just slow. Get low this good.
so we have like kind of rough stats. Max. Look at that. Whoa. I think so. So our max. Give me an eye. It's down there. Really doesn't. Not trying to ignore me now. My computer. Whoa. Like bad lipstick. Our min is 24. Actually, yeah, what do we want to do?
Arbitrarily delete those from the data set.
Oh, you think so?
I think that's no. Well, we need to divide each of those numbers by 10 because 10 spaces.
We can do that at the end.
That's much. The average is still the same. I already got it.
Alright, now do the average.
Oh, you got the average?
Remove the highest and lowest and see the average. Remove those outliers.
The average I got was 2.6.
2.600?
After you divide by 7.
Yeah, 2.6
Yeah, 2 on the dot.
on the dot. Yeah. Mine's hidden over here. Yeah.
Then pull up your
26.00, something like that.
So that's pretty good.
That's pretty good, right? How close is it? How close were we to?
2.60 over 2.65. Oh yeah, you're right.
2% error? Okay. Yeah, what did we have? 2.65.
What do? You do 0.05 over, which is
1.8% error,
yep, that's what I'm guessing.
right? 1.8%. How do we feel about that?
I can live with 2% error.
2% error. Pretty good. Where's the error coming from?
Air resistance, we don't know how to use the timer for it.
The timer. But we got lots of times, so sooner or later, law of averages is like, even if you're bad at measuring something, if you measure it a whole bunch of times, you'll get the right answer. The average result will be correct.
How are you holding?
You think air resistance drag?
How are you holding? Were you holding it in a way that was creating friction at the base?
I was not creating friction. Yeah. Yeah. But we had political differences between me and the pendulum, so there was social friction. All right, so we had, I want this one back. I know it is cold, but we got it. We need science. We got. Pretty good. So, do you think the fact that we simplified the pendulum, because really what we did was we said the time period was this like simple pendulum, like linear approximation. Do you think that we should have included more terms? Like we should have included drag, we should have included friction, like do you think that that is causing that 2% error?
Where did we do theta?
Where did we do theta?
Yeah, you circled the equation. I didn't think we used any angles.
When we said natural frequency is root G over L, then really what we did was we said the solution to the problem is that theta double dot is always equal to something times theta. That's our differential equation. So we skipped a lot of steps, but the main thing was like we assume that it's a linear differential equation, so it's going to have a constant natural frequency. But that's different. What we saw last time is like for large angles, that natural frequency changes. Yeah.
Well, I was going to say for the question you asked before,
Yeah.
since we were using a small angle for our pendulum, I don't think that it's super necessary.
Yeah.
At least the approximation would make it.
Yeah, for the most part, we had a small angle, right? And, with the magic of YouTube, right? We kind of get like maybe 5 degrees, maybe up to 8. And at least from what we had seen last time, that was well within like the small angle approximation. All right, I think we're caught back up. So there could just be measurement error, like maybe, but every time that got reported has at least 2 significant figures, like after, so it's not down to the millisecond, but tens of milliseconds. So at least like measurement, maybe our reaction speed is a little off. But we're trying to measure 27 seconds, so 27 you can probably get within a couple milliseconds, right? Or tens of milliseconds. What do we think? Is it all, are we missing terms in our differential equation, or is there something? Air resistance? Do you think that air resistance would change the natural frequency by 2% for the time period? You don't think so?
Especially when it's not moving fast.
It's not moving that fast, right? Assume the class is a vacuum? Yeah. That's what we did, right? We assume that it's a vacuum. Yeah. How well do we know the length of the pendulum?
Not very.
Not very. It's pretty approximate. How off do you think it could be?
Wait, how tall are you? Are you saying you're 5'9", but you're actually not as tall as 5'9"?
I am 5'9". I used to say 5'10" until I got multiple measurements telling me that I am not 5'10". So I'm like, all right, I'm 5'9". So yeah, I've already gone through that.
5'9" and a quarter, 5'9" and a half.
So within half, maybe 5'9".
Well, like
I don't know,
you just like approximated.
Also, I'm holding it to the top of my head.
I'd say maybe
You're wearing shoes.
plus minus an inch.
Plus minus an inch.
You're wearing shoes. You're taller in the morning than you are in the evening.
Well, is the length go to the top of the mass or the bottom of the mass?
Yeah, and
That's the
also,
center of the mass.
Is the mass of,
yeah, like where, as we're talking about like the mass.
is it showing up on the thing?
Yeah, as we're talking about the mass, I measured from down here. Is it actually like somewhere in here, like where the end of the pendulum is?
Because usually the approximate like a point mass to say like center of gravity.
So then,
It's another inch.
Yeah. So we might have had some error in the L measurements. If you can call it that.
try this. So we know, so what is it? 2 pi over root G over L plus Yeah. Now it's not as helpful. Let's say 2 inches, right? So one way we can, I mean, there's other ways that you can do like a stats, like take the partial derivative of this thing with respect to L and figure out how well, but a quick engineering way to do it is just like, all right, if it's 5'9" plus 2 inches or 5'9" minus, so if it could be 5'11" or 5'7", then what's the max min? Like what's the range of predictions that could end up being? And that's like a nice way of just getting like, how accurate do I think my model really is based on the measurements that I can make? Sorry, that one's delta t. You're right. So what do we think? I'll throw this one. What is 212, 1/6?
1/6. I got you.
So it could have been 2.7 or it could have been 2.6 seconds. Are we still on the low?
We're still below the lower end of that, yeah.
We're within.
I mean, by 0.01.
Oh wait, you're right. Where's our? Where did we calculate? We got 2.6. Yeah, and we're still a little outside. Yeah.
We didn't have those extra 2.7.
No, we got rid of it.
No, we didn't.
Not in this one, at
Actually,
least.
you know what? What if you did get rid of those outliers? What if you get rid of the highest and lowest value and consider them outliers and took the average of them?
You think the 24?
And the 23.
Well, the 23.9 and the 27.14.
Yeah. Delete them. Or like comment them out.
And then, in the interest of science, we'll keep them. And then 24 you want to get rid of?
No, the max.
Oh, the max?
27. You keep the 26.
It's slow, remember.
Huh?
We're watching it 2 seconds behind which is
26.2.
Now that puts us within.
Yeah, now we're right in the range, right?
Hey, you started writing stuff already.
I started what?
This is how science goes. You need some kind of prediction of like some kind of hypothesis of like, I think this is gonna work, and then when you measure it, it's like nothing worked. Nothing. The world doesn't make sense anymore. But as you process, you get to a point where it's pretty satisfying. So at least what we have is like we're doing pretty well. And we did not include drag. There's no friction. There's no nonlinear effects. There's no like all we did was say it's tension and gravity, and that's it. And we made a pretty accurate model for this. If you were like watching the actual like angle of like how far the pendulum's moving, there's visible decrease. You can see that it's not swinging as far as it used to be. Like the magnitude starts decreasing slowly. but that doesn't really change like our measured time period. All right, cool. Now we'll go to like the back side of E2 and I'll stick it out the window because bigger is better, and do like 3 stories for the pendulum. Then we'll still have to like measure how long it's going to be. But 3 stories, how tall is 3 stories? How long is that pendulum going to be?
I think the code is like 10 feet tall.
I think it's taller than 10.
These have got to be
Well,
taller
this
than
is
10.
there.
Sorry?
This is across the building, I'm pretty sure you might.
36, yeah. 12 feet.
We just stand on each other's shoulders if we know
No,
this
this
height.
Oh.
Yeah, we're
Yeah,
down.
we are currently below. Like,
We're below sea
Yeah, I
level.
am.
They're in like the door.
We're not below sea level. We're in northern Connecticut. Southern Connecticut is below sea level. All right, but if you're watching online, sorry, we're leaving the classroom. We'll see you next time.